I'm sure a lot of people here are coming from more of an electric vehicle background. You're really concerned about inverters and PWM and current ripple and all this good stuff. So an inverter PWM output is effectively a bunch of square waves. And if we remember, our square waves had a lot of harmonics. So PWM really likes to introduce harmonics. A motor acts as a filter to remove a lot of them, but it's only removing them in the current. And if we remember from our last example, our voltage had a higher harmonic content, a little foreshadowing for what we're going to see here right now. So this current ripple, this voltage switching, is reflected in the RMS and reactive power, and we're going to look at that in a moment. And again, for consistency, 500 kilohertz sampling, 50 kilohertz filter. Let's jump in. So, okay, what if we take our voltage and current and we calculate power just how we always have? P equals IV, just point by point. And we start to see this power, and we got our average power. I'm going to draw a very poor straight line, so I apologize, that's ugly. And I've got a 0, an average, and my average is 32 kilowatts. Well, I have peaks here at 300 kilowatts and negative peaks at around 100 kilowatts. And we see this reversal at the switching rate. So we have this really high frequency content in our power because of the influence of all the inverter switches. And if we, again, remember back to that statement I made originally, power oscillations indicate there's a significant amount of reactive power. What we have here is very large, very fast power oscillations. And again, this just justifies that need for an RMS voltage and an average power. We take this oscillatory thing, we look at it over a single cycle of a sine wave, and we can see that this averages out to this nice clean value. Cool. Oscillations, a lot of reactive power. We need averages, we need RMSs. So we take that data and we run our calculations. And we get RMS voltage, current, reactive power, apparent power, and real power. And if we run the numbers, we get a IRMS, a VRMS. Note this 210 again. We see our apparent power is 60 kVA, our real power is 32 kilowatts, and our reactive power is 51 kVAR. Our reactive power is greater than our real power. And again, this is where I get a lot of questions, and we'll touch on some of this in a moment. Our fundamental phase, if we remember, this is the phase shift between the 0 of my current and the 0 of my voltage. So this one's not changing. And my power factor, my P over S, 0.538. Now, all of these were calculated with the exact same equations. S equals IV, IRMS and VRMS equations, Q equals S squared minus P squared. So we see that RMS is going to have a huge effect on Q. Okay, so this was the wideband. This was the 50 kilohertz example. So what if I filter this? So in this example, we take the same data, very important, this is the exact same data, and instead of a 50 kilohertz filter, we now apply a 2 kilohertz filter. And if we look at this, we can see, all right, my voltage has a lot less oscillation. My current's got a lot less oscillation. And my real power has a lot lower amplitude and a lot less oscillation. But we still have that reactive element. We still have a lot of oscillation going on, so we're not at 0. We do our calculations again, and we can see that, okay, my apparent power has come from up here down to here. My reactive power has come from up here down to here. This is a good sign. We have fewer power oscillations. And again, the exact same equations we ran on a higher sample rate. IRMS, 287, VRMS, 134, almost 100 volt drop. Our apparent power, 38 kVA, down from 60. Our real power, the same, because real power is real power. Reactive power, significantly decreased. And now we have a fundamental phase that's the exact same again, because our 0 timing is not changing. Now our power factor, our P over S, is 0.845. exact same equations, different interpretation of the data. So this is interesting. Now, for completion's sake, let's take that a step farther. And now we take the fundamental, and I apologize, I didn't change the color of my voltage. But we can see that we have these very clean sine waves. We have this, this power that's got this nice oscillation to it. And if we do our equations, again, RMS voltage, current, apparent power, real power, reactive power, we measure our values, and we get even a little bit more decrease. So 2 kilohertz got us most of the way there, but not all the way to the fundamental. And what we'll find is the exact same equations. We've run this fundamental calculation to really isolate the fundamental RMS voltage and current. That fundamental is if everything was a pure sine wave, that would be our value. Same real power, same phase angle, but again, a lower values on RMS values, reactive power, apparent power, and our P over S value, again, has gone up a little bit. So, let's take our comparison table. Power does not change because real power is watts, it's work. We can measure real power very accurately. But RMS, apparent power, and reactive power, these kind of more interpretive results, trains drastically with filtering. I mean, absolutely changed drastically. And to say one is right and one is wrong kind of matters what your job is. And it matters what you're comparing to. And when we start filtering these things, we're removing that oscillation. But the guy who's doing control development or PWM development might want all of that content because they might want to see how their switching frequency influences that reactive power. The guy in the power grid might only want the fundamental. Or if you have a model you're comparing to at 5 kilohertz, or a consumer's or customer or a supplier's equipment you're trying to compare to with, a 5 kilohertz filter, you need to know these things. Because if you want to compare the 2 kilohertz filter with the 50 kilohertz filter, you're going to ask a lot of questions because these numbers are drastically different. So please just keep in mind that you need apples to apples when doing analysis, whether it's models, whether it's previous data, whether it's historic data, whether it's different equipment. If you start asking questions, you can probably start figuring out the answers to what you're looking for. So my conclusion here, reactive power and RMS are complex beasts. I don't expect anybody to walk away being an expert after this, but I really encourage you to start asking questions. And when you go to measure these events, consider what you want to look at and how much content you want to understand before you acquire data. Because if you start asking those questions, you can set yourself up to compare apples to apples or make sure you're comparing one correct value to another. Always remember that high frequencies, be it harmonics or switching frequencies, are going to introduce reactive power. They're going to introduce oscillations into the system. And naturally, I get a chance to pitch my little baby here. Because the HBM equipment records data at the high sample rate, a ton of control on the filters you apply, you can run really wideband or high filter data, or you get high bandwidth data, and then you can filter that down in the post process to figure out where you want to operate, or you can run those fundamental equations to get that fundamental values. So we give you the option to look at one or more of these values. So you really can compare to your models, compare to your customers, compare to whatever you need to compare to. Before I thank you guys for your time, I just want to mention that